Hi everyone, and welcome to this video. Today I'm going to talk about SyNAPSE, a new project from the CMU-PT program on synthesizing network accelerators. My name is Fernando Ramos. I am an associate professor at the Instituto Superior Técnico, or IST, from the University of Lisbon. I'm also a researcher at UNESCO. I'm the Portuguese co-PI for this project. Luís Pedrosa is the lead PI from the Portuguese side. And we're lucky enough to have Justine Sherry as PI from Carnegie Mellon University and Ruben Martins also from CMU as co-PI for this project. So in this project we propose to leverage program synthesis techniques to automatically generate network function accelerators, taking advantage of modern reliable network equipment. Before I present the project, allow me to briefly contextualize it with some background on how networking infrastructures have been recently evolving. To, on the one hand, make sure that we're all on the same page, and on the other hand, to emphasize the timeliness of this work. I would ask you all who are already familiar with this topic to bear with me for some minutes. The context of this work is network function virtualization, or NFV. As many of you may know, traditionally in computer networks we have dedicated network functions. I'm talking about firewalls, web caches, DPI boxes, proxies, etc. as dedicated appliances. This equipment is prevalent in today's networks, so some studies have concluded that there are as many middle boxes in the network as routers and switches. This dedicated hardware is highly performant, but offers little flexibility other than basic configuration and is often very difficult to manage, which of course leads to high costs and limits innovation. As a result, the people who run advanced networks, both in the data center and within network operators, have been looking at more flexible approaches. One such approach is to implement network functions entirely in software, with all the flexibility that comes with that, and run them on commodity server hardware. As you can imagine, the challenge here is performance. We thus have today a clear trade-off between performance and flexibility. And since network functions are now running in general-purpose processors, let's recall where we are in that respect, just for the sake of completeness. I'm sure we're all familiar with these two important personalities, even if not with faces, surely with their names. Gordon Moore is the well-known American businessman and engineer, famous for being the author of Moore's Law. Moore's Law made the observation that the number of transistors in an integrated circuit doubles about every 2 years. Informally, it told us that we could expect the speed and capability of our computers to increase every couple of years and be cheaper. Robert Dennard is an American electrical engineer that, among other things, invented the electronics that were the basis of DRAM. His scaling law, named after him, Dennard's scaling, states roughly that as transistors get smaller, the power used stays in proportion with the area. So, what this means is that if transistor density doubles, power consumption with twice the number of transistors stays the same. These two gentlemen are still alive and well today, fortunately, already in their 90s or close to that, and they share this common characteristic. They have survived the laws that bear their names. I'm also pretty sure that this graph is familiar to many of you. This is the graph that shows the steady exponential increase predicted by Moore's Law, at least up to around 2003, 2004. Moore's Law held for these many decades. It began to slow something around 2003. Dennard's scaling, in fact, began to slow significantly in 2007 and faded to almost nothing in 2012. By now we have roughly 15-fold gap between Moore's prediction and current capability. This was an observation, by the way, that was made by Moore himself back in 2003. That was inevitable this to happen. The main experts in the field have been reflecting and arguing for the need of new approaches. One approach considered promising, and the approach that we follow in the SyNAPSE project, is that of domain-specific accelerators, or architectures. Domain-specific architectures are architectures that are tailored to a specific problem domain and offer significant performance and efficiency for that specific domain. Examples include GPUs, neural network processors used for deep learning, and processors now for software-defined networks. So we have, for example, for networking, we have domain-specific accelerators that are programmed with a high-level language like before. These domain-specific architectures can achieve higher performance and greater energy efficiency for four main reasons. They exploit parallelism for that domain, they're more effective in their use of memory hierarchies, they use less precision when adequate, and finally they target domain-specific languages that help in these optimizations. In the networking case, for example, we have the language P4 to program these network accelerators. So let's now focus on these specific network function accelerators. As we've seen, until very recently, an operator had for its network functions only two options. You buy very expensive and inflexible but performant middle boxes, or you would write the NF software to run in commodity servers, trading flexibility for performance. Developments in CPU-based packet processing enabled a significant increase in performance gains by means of kernel bypass techniques like DPTK or NetMap, and the exploration of multi-core processing also helped. With these techniques, we were able to multiply by 10 the performance. So instead of having gigabits per second packet processing as in traditional CPUs, we are now able to get, with these DPTK technologies, for instance, tens of gigabits per second. So it's a significant increase. More recently, we've seen the developments on programmable network devices. And with these devices, developers can use new classes of smart network equipment with programmable packet processing pipelines, which can guarantee line rate operation. You no longer have the full power of a Turing-complete program, usually, but you can specify how to pass packets and how to process them in an expressive series of rule-based pipelines. Examples include NPU-based smart NICs, as the one I present here, that lead already to hundreds of gigabits per second capacities. At a larger scale, we have programmable switches or programmable ASICs, such as Intel or Barefoot Tofino, that achieve terabit per second scale packet processing. So we now have this plethora of network accelerators. So what's the challenge? Well, with this array of network accelerators, we have a problem, is that they are programmed with different domain-specific languages. And these languages are tailored to different target architectures, these new domain-specific architectures. These devices are much harder to program than your standard server. You don't use Java or C to program these. They often require deep knowledge of the internal hardware constraints to take full advantage of their capabilities, requiring you to program in Verilog, for instance, for FPGAs, or domain-specific languages such as NPL or P4. The inherent limitations of their functionality also limit the sort of computation available. This is where SyNAPSE enters. So let's recall that on the one side, developers can use these new classes of smart network equipment with programmable packet processing pipelines, which can guarantee line rate operation. That's high performance. But you no longer may have the power of a Turing-complete program, so you have less flexibility. And also, these devices are much harder to program than your standard server. On the other side, we implement network functions in software. With all the flexibility that comes with that, run them on commodity server hardware, program them with the languages we know, but we lose on performance significantly. So the question for the operator is, what to choose? In SyNAPSE, we ask a different question. Why not have the best of both? For this purpose, we propose a synthesis framework that takes as input the network topology and a software network function that's typically developed in C, for instance, mapped onto it, and produces an output P4 code to program the switches and the smart NICs, as well as the code that runs on the controller, which typically is in C, in Python, or in Java. So we take NF code, we take topology, and we get the code necessary to run in the network accelerators. Under the hood, SyNAPSE follows a three-stage pipeline. The first is to analyze the network function using exhaustive symbolic execution to build a sound and complete model of NF functionality, which looks like a decision tree. This analysis builds on prior work from the PI Luis Pedrosa, and it's also already ongoing work. We then use a search-based synthesis algorithm to transform the model into an execution plan by converting abstract functionality into concrete operations, either on a network device or in the controller. In this stage, for example, state accesses and other packet operations are mapped onto switch operations, including table lookups or access to register memories, all depending on the device's capabilities and constraints. As the final step, we generate the final code from the execution plan, outputting the final P4 and the final SDN controller code ready to be compiled and deployed. We don't stop here. The synthesis process is guided by a search metric which maximizes performance. By default, we can maximize the performance for worst-case traffic, but this may not be ideal for all circumstances. With that in mind, we can better guide the synthesis process by using profiling data to optimize for typical traffic rather than worst case. With this in place, we envision an NF lifecycle with continuous deployment, reprofiling, and resynthesis. This allows the network to evolve and adapt to new conditions and re-optimize to better handle changes in the workload. You may ask, why us? Why and why now? We have a great team on this project. I'm really fortunate to be surrounded by these folks that brings together skills and experience from a variety of backgrounds. So lead PI Luis Pedrosa brings to this project his experience with program analysis as applied to software and apps. PI Justine Sherry brings their experience in developing accelerated NFs using smart network devices. And co-PI Ruben Martins, in turn, brings his experience in program synthesis. And I, for my part, share my experience in network architecture and software-defined networking. We also already have some students on our team. We have Francisco Machado. He has started his master's thesis on this project. We'll focus on the synthesis engine and P4 code generation. And we have Francisco Pereira, finished his master's thesis recently on a related project involving synthesizing parallel NFs and intends to continue as a PhD student. We also plan to hire an additional PhD student and other master students very soon to pick up the slack and to help us build the test bench. So we meet regularly, like every week we meet with the entire team. That's all PIs and students. We also have student one-on-ones as needed. And 2 months in, we can say that we already made some progress. We already prepared the initial SyNAPSE framework design. And we also already have some prototype code for analyzing the NF and building the functional model I mentioned earlier. And also some code for translating that back into x86 code, which will be useful for the network controller. We are working also on our first paper, and we have a related master's thesis completed. Of course, it didn't start with the beginning of the project, but it's very much related and will be integrated too. As I alluded to when I introduced the team, we have two parallel development tracks. That's developing the search-based synthesis engine and P4 code generation. That's led by Francisco Machado, and developing all the infrastructure behind the optimizing resynthesis. That's led by Francisco Pereira. All 4 PIs are involved with both of these fronts as well. I close by leaving a longer-term view for SyNAPSE. So SyNAPSE, and specifically now, targets a specific use case, generating code for a P4 switch and an SDN controller. But our long vision entails a general approach to synthesize code for multiple network accelerators. We are talking about traditional x86 processors that take advantage of multi-core and other acceleration techniques, smart NICs with different architectures, that's FPGA-based, NPU-based, PISA-based, etc., and even OpenFlow switches, like traditional SDN-based switches. Having this plethora of accelerators, we also envision the partitioning of network function code to run across multiple such platforms. So we envision a network with multiple of these platforms and then taking best advantage of the different performance programmability trade-offs in each. We also plan to automatically generate any necessary load balancers to distribute traffic accordingly. On that note, I close and I thank you for listening and watching. I'll see you next time.